Maybe I'll start.
Okay. So today's speaker is Andy Mackenzie. Andy Mackenzie was here last year as a HANA professor, and it's one of the duties of the HANA professor to give a departmental colloquium. Unfortunately, Andy's host was sufficiently disorganized that the colloquium didn't get organized until now. So this is last year's HANA colloquium by Andy Mackenzie. Good news is we've managed to get him to come back and visit. He's around this week and next, and so I encourage those of you who are interested in talking to him. Let's see. What did I have to say? Yeah, here. So Andy is a fellow. He's an FRS, which is Fellow of the Royal Society. He's an FRSE, which is a Fellow of the Royal Society of Edinburgh, and he's a Fellow of the APS. He's also a director. He's a director of MPS, which is, I guess, the Max-Planck Society. And he's won a number of prestigious awards, including the Mott Medal of the IOP. And the IOP is the Institute of Physics, but not the one in Beijing, the one in London.
The little one.
What?
The little one.
The little one. So Andy is a very renowned and distinguished condensed matter physicist. He's famous for doing key and clear experiments that reveal emergent phenomena in interesting correlated systems, including exploring new phases of matter, quantum critical phenomena, and novel transport regimes. His work has been characterized by extremely high standards, by an emphasis on the importance of extremely careful control of the materials and precision of the measurements. Andy is also a wonderful person and a good friend of many of ours. So, Andy.
Thank you very much, Steve. Given some of the previous introductions Steve's done for me, I'm feeling very disconcerted at getting off so lightly there. In fact, that was great. And it's, of course, a huge pleasure. It was all to my benefit that it wasn't organized last year. It gave me an excuse to come back, and it gave me an excuse to come back and join in this incredible celebration next week for Ted. So it's not accidental that I'm here right now. So given that happy sort of coming together of times, I thought that I would give you a colloquium today which is supposed to start way back at the beginning, which, as you're going to see, is a long time ago, but tell you about a technique which continues to evolve and I believe continues to be important today and will continue to be important in the field tomorrow. So I'm going to be attempting to give you a flavor of all that. Specifically, we'll talk about the historical development. We'll talk about the way that the Haas-van Alphen effect, or quantum oscillations, give you a unique spectroscopy if you want to decide whether or not something is a Fermi liquid. I'll mention something about a Fermi liquid as we go. One of the things I believe is that the Haas-van Alphen effect, or the need to do it, has been, and understand it, has been an incredible driver in many ways in the field. It's been a driver for experimental technology in materials physics. It's also, as I'll show you, been a driver for some rather profound theoretical developments. Then I'll close in the last few slides by giving you some ideas of future directions, and hopefully by the end the conclusions will be self-evident. So let's cast ourselves back to when Ted Geballe was 10 years old. In 1930, working at Leiden, de Haas and his, I guess, assistant or graduate student, Van Alphen, were studying the torque response of the magnetization from bismuth, single crystal bismuth, and they made this very surprising discovery that the response wasn't, if you like, DC, but had very pronounced oscillatory behavior. So this oscillation is now known as the de Haas-Van Alphen effect, but as I'll show during the talk, the oscillation fundamentally comes from an oscillation of the density of states at the Fermi surface. So actually, more or less, any property of a metal will oscillate, and that's why there is this general terminology of quantum oscillations used to describe it. So I'm going to end up going smoothly between DHVA, de Haas-Van Alphen effect, and quantum oscillations. Just be aware that when I say DHVA, I'm really referring to the subset of these phenomena which is detected by studying the magnetic torque or the magnetic susceptibility. So they did this work, de Haas and Van Alphen did this work at Leiden, and in fact, as you know, Leiden is a real powerhouse of condensed matter physics. Kamalianis liquefied helium and discovered superconductivity there. And I read in a biography of Kamalianis the very kind of sobering statement that de Haas was regarded as a failure. He was regarded as the guy who didn't quite keep the tradition up in the same way that Kamalianis had discovered. Well, I would kind of like to fail as badly as he clearly failed by discovering this effect. So Leiden, as a historical place, has a museum in the physics department. And because of superconductivity and the helium story, they have lots of exhibits about these discoveries, and they have part of the original helium liquefier, and everybody crowds there. That leaves lots of space for me to go in the other direction and take a picture of this, and that's the electromagnet that these data were taken in. So 2 Tesla electromagnet that was being used by de Haas and Van Alphen nearly 90 years ago in Leiden. So maybe one of the reasons that, one of the decisions that de Haas took, I have no idea why, was that having discovered this effect, he did very little work on it afterwards. So he's the discoverer, and correctly his name goes to the effect, jointly with Van Alphen. But the guy who really pioneered the effect devoted, I was going to say a lifetime, but it's actually about 2/3 of a lifetime, scientific lifetime, to this effect, is David Shoenberg. And I say that because in his life, David wrote 2 absolutely monumental books. One of them is very little read now, but it's a monograph on superconductivity written in the late 1930s that I believe Bardeen cited in his Nobel lecture as the book that he was reading when he was getting into the study of superconductivity. And it's still to this day an extremely interesting book to read because Schoenberg lays out the thermodynamic foundations of superconductivity and makes some extremely profound statements about what basically has to be going on in some way. So guys like Schoenberg and the Londons knew a lot in the 1930s. They just didn't have everything set out, and it's very interesting to read that. It's also extremely interesting to read his discussion of type 2 superconductivity, which Kubrick had discovered, and he has a very rational discussion of whether this is a junk effect of filamentary superconductivity or whether it might be a thermodynamic phase. And again, these are very, very interesting things to read to this day. So that was one of Schoenberg's books. The other one is this, Magnetic Oscillations in Metals. And this book, for a long time, was a hardback book that was out of print. It's now been reprinted as paperback. And around the world, there are many kind of dog-eared copies of this famous Schoenberg book. That's my own copy. You can see it suffered from being multiply opened. I then failed to bring it with me when I came here and had to borrow Steve's copy from him last night to check up a couple of residual disputes we were having on some details of it. But it really has anybody laid the foundations of a field as crisply in a single book as Schoenberg has done here. There's been no text on the de Haas-Van Alphen effect since, and this was written in 1984. And that's because, by and large, there isn't much need for one. It's not an easy read, it's not easy to understand relative to his first book, but it's a fantastic piece of work. So, David should be, in my opinion, more famous than he is. This is work, this is absolutely profound work that he did his whole life. But the other guy, his friend, the postdoc who he did a lot of the work with in the 1930s, doesn't suffer from that issue. So Landau was working, so Schoenberg spent most of his academic life in Cambridge. He was British-born, but the son of Russian immigrants. And therefore, or maybe not straight therefore, but he was very closely connected to Kapitsa when Kapitsa had the laboratory, his laboratory in Cambridge. And Landau was a visitor, so they were essentially postdocs at the same time in Cambridge. And then later, Kapitsa was repatriated to Russia by Stalin, and Landau as well. And but Schoenberg was a British passport holder, so he was asked by Kapitsa to go to Russia in the late 1930s, and astonishingly he did for 1 year. So he spent a year at the new Kapitsa Institute, and we'll return to that story later. So anyway, so Landau was involved from the start, and at the same time, same year that de Haas and Van Alphen were working experimentally, Landau was working completely independently, theoretically, on the problem of using the new quantum mechanics to quantize the motion of electrons in magnetic fields. So he worked with the free electron gas, and I'm just going to illustrate it here in 2 dimensions for simplicity. So if you have a moving electron in a perpendicular magnetic field, it'll undergo classical cyclotron motion, circular motion in 2 dimensions. The equivalent quantized wave function in real space, where it's not so often plotted, looks like so. It's just what you would expect, at least at the regime of high quantum numbers where the correspondence principle works. It looks like a fuzzy quantum broadened version of the classical orbit. Right, so that's how the Landau wave function looks in real space. I'm going to flip between real space and K-space as we do this description. Hopefully, for reasons you'll appreciate in a moment. So now let's go to K-space, which I hope most of you are familiar with. So in zero field, in momentum, this is Kx and Ky. In momentum space, you have this whole series of discrete K levels, each of which can be occupied by 2 electrons. And you have this completely remarkable surface that sits in a metal in momentum space and acts as a singularity, demarking the filled states from the empty ones outside. I'm working in 2D, so it's a line, not a surface, but people always think of it as a surface, or refer to it as a surface. The K-space version of the Landau quantization I just showed you is to take K and make it no longer a good quantum number, and to produce a series of orbital states which are multiply degenerate. So you have to think of these K states condensing, not condensing is the wrong word, but forming the appropriate the closest Landau level to where they originally were. And then there's a big degeneracy factor that you can work out. And here we're sketching Landau levels in gray, which are filled states, filled with the requisite number of electrons, Fermi surface, and then a couple of yellow Landau levels unoccupied outside. Now, as you increase the magnetic field, what Landau was able to show is that the radius in K of these Landau levels increases as you increase the magnetic field. So all the Landau levels that you quantized into are moving outwards as the field goes up. And straight away you can see qualitatively where oscillations must come, because something periodic in some form is happening as those Landau levels cross the Fermi surface and depopulate. But if the very intuitive way to look at this was given to us much later by Onsager and Lifshitz, working entirely independently, one in the Western world and one in the old Soviet Union. And we'll come to exactly what Onsager did in a minute. It's incredibly insightful. But what he stressed was that, okay, one of the things he stressed is I showed you a moment ago that the K radius of these Landau levels is quantized. It can be there, then there's a gap and another one and another one. At high, when the correspondence principle is working, if you've quantized K, you've quantized the real space radius as well. So discrete K equals discrete R, and R is a magnetic length which goes as 1 over the magnetic field. So that's a very nice way for me to realize that the quantization is controlled by a reciprocal field controlled length scale, related to a reciprocal field length scale. And that's a much nicer way for my mind to see the fact that these oscillations are periodic in reciprocal field than many of the treatments I read in textbooks. Okay, but Onsager said something far more profound than that. So I was very lucky. I don't think this is actually digitized, not in a form I can find on the internet. So it existed in the library at St. Andrews, this paper. So this is my own scan of the photocopy I took of the paper. And it's in many ways one of the most remarkable papers I've ever written. So the first thing that will be surprising to you, written red, yes, thanks. I saw some amusement on Sean Hartnell's face there, which helped me. The first thing that will surprise you maybe is that Onsager gives his address as Cambridge. Very few of us associate Onsager with Cambridge, but he did spend time there. And I think that that's testimony again to the influence that Schoenberg was having. His experiments were such that he was attracting some of the world's leading theorists to Cambridge to work with him and to think about the theory of DHVA. So that's interesting for him. But then this paper contains one of the favorite phrases, my favorite phrases I've ever read in a paper, whereby we recognize a fundamental unit, blah, 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 equal to the flux from one of Dirac's hypothetical magnetic poles. So what Onsager had realized was that the actual condition for the flux quantization and Landau quantization came from a concept which is ubiquitous now in solid-state physics, which is the idea that you have exactly one flux quantum threading the real space area of the Landau orbit, and that was what was dictating the quantization condition. And, you know, I don't have proof, I'm not a professional historian of science, but certainly the way he wrote that makes me think that this is probably, or he thought it was new, that this idea of real space flux quantization was being introduced in this paper. Many people who will know the literature from then better than me, I'll be interested to hear if people have some remarks on that. But certainly it was a wonderful thing to see, and for me to see in a paper. The final interesting thing goes back to this geopolitical story of Schoenberg and Landau being out in Russia in the late 1930s. So Schoenberg told me that he had lunch every day with Landau. Actually, they would go off campus from this institute to one of their flats and have lunch. And one day, Landau didn't appear. And that's because Landau was being entertained by the NKVD in the Lubyanka that day. And famously, it took Kapitsa a year of very hard work to get Landau out. And Landau is one of the very, very few people who ever was arrested in the Stalin purges in the 1930s and survived the experience. But just before being arrested, he had written some big advance in the detailed understanding of DHVA. And Kapitsa and Schoenberg agreed that it was important for the world that this was published. But Landau was a non-person. And even publishing the paper in his name would be taken as a provocative act, and it was going to be a dangerous thing to do. So they decided that Schoenberg would publish a long paper on the experiment. This was a paper published in 1940. That he would put an appendix citing Landau for the theory, but that way they could give Landau the credit for what he'd done without really drawing attention to him in the headline of the paper. So this paper by Onsager, if you read it, references Schoenberg and Landau in the main text, but then has it citing a reference Schoenberg only, and that's the reason Landau did not officially exist at that point in time. So if we go away from the stories to the physics, we now know that as we increase the magnetic field, and in this pathological case of two-dimensional system at fixed chemical potential, we would see sawtooth oscillations. In reality, you never do. You see something much more with much less harmonic content. That oscillatory behavior is periodic in reciprocal field rather than standard field, and that's a consequence of real space flux quantization. So at that point, people had much of the artillery that they needed to start using the Haas van Alphen as not just a nicety, but as a tool with which to understand solids. And Schoenberg and a number of colleagues, probably 5 or 10 colleagues of other labs around the world, spent about 30 years determining the Fermi surfaces of all the simple metals. And this was a Herculean task. And what they were doing to do that was to use a K-space version of this quantization condition that both Onsager and Lifshitz also stressed. And that relates the frequency of the oscillations you see to special areas of three-dimensional Fermi surfaces, which are areas where the Fermi surface has zero derivative in the direction perpendicular to the applied field. I don't want to go into that in too much depth. But here in copper, if you have the field in this direction, you're seeing that orbit, which is known as the neck orbit, and you're seeing that orbit, which is the belly orbit. And what you see experimentally are the two of them superimposed. So that's a small K-space area, so it's a long period oscillation. That's a much bigger one, so it's a short period oscillation seen on top. And these guys just worked and worked and worked to get this all done. So it was, what they discovered though, or worked out, was that they were able to get far more information out than just topographical information about Fermi surfaces. And the reason for that comes when you look at this slightly hicky simulation of, these are high Landau levels crossing the Fermi level. And in the first graph here, we're working at a temperature low enough that the Fermi-Dirac function is narrow on the scale of the Landau level separation. That means that only one Landau level is depopulating at a time, and whatever oscillatory behavior you're going to see, you're seeing close to the maximum that's thermodynamically available to you. If you go up to a higher temperature, where the Fermi-Dirac distribution is broader, then you are gradually depopulating a number of Landau levels all at the same time, and just qualitatively, you can imagine that that smears out the signal that you're going to see. So the de Haas van Alphen effect is extremely temperature dependent, and even in the old days on traditional metals, they had to get technology going at around about 1 Kelvin in order to do this and get the right level of precision on all the work that they were doing. And here I'm just restating that this is a good way to restate the fact that the density of states is what's oscillating, and therefore all physical properties will oscillate to some level, not just the magnetization. So I think that work, many of the things that have been done in de Haas van Alphen have suffered a little bit at the hands of history in terms of their significance. Now, the fact that metals have Fermi surfaces is really a remarkable thing, and the fact that it was possible to measure these with this intense burst of work over 30 years was also remarkable. But one of the reasons that it's ended up being a little underemphasized is essentially a fallacy. It's entirely false. And the point is that these formulae that I was showing you were developed in the absence of electron-electron interactions. So this was all free electron gas, or free electrons in a periodic potential work. And so that Fermi function that I was showing you is the Fermi function for free electrons at t equals 0. But now imagine in your mind that you went to an electron liquid instead of an electron gas. We know that in terms of the original electron eigenstates, the distribution overall gets very strongly broadened by the interactions. It retains a little discontinuity, but that discontinuity can be extremely small. And it's that physics which kills the ability of many spectroscopies to decide whether there's a Fermi liquid or not. They're really more sensitive to the one electron eigenstates. And when you look at this, you would say, oh, wait a minute. Is this not telling us that the de Haas van Alphen oscillations will be hugely damped even at t equals 0, because the interactions are playing an equivalent role to temperature in some ways. And that, of course, famously is not true. One of the great benefits of saving Landau's life was Fermi liquid theory, one of the most remarkable theories ever written. And what he showed was that if you didn't think about the liquid excitations as electrons, but as many-body superpositions forming quasi-particles, the quasi-particles could be thought of as obeying the same full drop in the full Fermi function as the original electrons did, even though the interactions, in fact, had changed everything for the electrons. And so this was not quite the way that Fermi liquid theory was expressed when it was first written down, but this is a known ramification of it, and of course it's a profound statement. So that then came out when people started studying or understanding how they were going to use the temperature dependence of the oscillations quantitatively to measure things like electron effective masses and decide whether what they were looking at was a standard electron or some kind of a heavier electron. And what they famously do, we all do it when we're doing these experiments, is they see if the data conforms to that red line. And that red line is this particular functional form. And the argument of the function is the effective mass, temperature over magnetic field. So experimentally, you hold the field or the field range constant, you vary and measure temperature, and you fit your data to the function, and the fit parameter is the effective mass. So you're able to deduce the effective mass. And that, I think, is very well appreciated. What's less well appreciated, and the other thing to say is that when you do that, you typically get extremely good agreement. And this is from Suchitra Sebastian, an alumna of Stanford. But we've all in the field taken the data like this and shown that it agrees with this function very accurately. So that's known, but what is less appreciated and less emphasized is that the existence of that x upon sinh x functional form is entirely dependent on there being a perfect Fermi-Dirac distribution for the quasi-particle, for the excitations you're studying. And that's really important because that says that if you take these oscillations and you study their temperature dependence and you agree with this curve, that's the existence proof of a Fermi liquid. You have these quasi-particles with the enhanced masses, and they're obeying this function which tells you that they have a perfect Fermi-Dirac distribution. And there are many ways one can think of, and I'll come to one at the end, where one might see quantum oscillations, but not see that temperature dependence. And in those circumstances, that's the best possible experimental probe you can come up with for having a metallic state which is beyond the paradigm of Fermi liquid theory, or a state which is beyond the paradigm of Fermi liquid theory. So quantum oscillations, the Haas van Alphen effect, is an often underappreciated existence proof of the existence of the Fermi liquid. And as such, it has a really special place, I think, in physics. So now I'm going to move on to work done by my PhD supervisor, Gil Lonzarich, and published just a year before I joined his group. Because people had discovered materials with extremely high linear heat capacities, and they were calling them heavy fermion materials. But if you naively looked at the heat capacity, it looked like there were quasi-particles here of masses 100, or even 150, 1,000 in the most extreme cases. And when that was going on, nowadays we look back at this, and they're called heavy fermions, and everybody just takes it absolutely for granted that this is it. Okay, it's a heavy fermion liquid with very heavy quasi-particles. But at the time, if you go back and read the theoretical literature, there was no shortage of imaginative ideas for how it would be impossible to have a Fermi liquid obeyed with quasi-particles of these kind of masses and all the kind of breakdowns that could be happening. So Gil and Louis Taillefer, when Louis was Gil's postdoc, did this wonderful experiment on UPT3. In my opinion, this is one of the single best experiments of 20th century condensed matter physics. So they found the oscillations, they did the transform, they found all of these quasi-particle peaks, and they assigned the masses to each peak. So what you're seeing there is what Gil, I'll have it on the slide in a minute, he always says to me, this is particle physics in the condensed matter laboratory. This is a little bit like a resonance you would see in a particle physics experiment. Our universe is infinite, right? We have an infinite number of ways that these many-body quasi-particles can form. But they were showing there that this was, killing any claim that it wasn't a Fermi liquid. And they're showing that you've got these many-body quasi-particles, masses up to 110 electron masses. These things only very faintly remember their origin as electrons. And yet there they are obeying this perfect Fermi-Dirac statistics and acting just like heavy electrons. So in order to do this, it was an experimental tour de force at the time. They had to do, all of this was deduced from data taken at below 20 milli-K. And this really wasn't an easy experiment. And I think, there are kind of, internationally, I also believe that Gil, like David Shoenberg, has been under-recognized, particularly for this experiment. And timing is everything. There were two things wrong with the timing here. The first is they did the experiment too soon after the discovery of all these heavy fermion compounds. They didn't give the theorists enough time to come up with enough wrong theories that they were going to scotch. They should have certainly given them more opportunity. And the second...
They come up with a lot of wrong theories.
Pardon?
We were very efficient.
You were efficient. You had quite a few wrong theories. Okay, good. You've been pretty efficient at hiding it afterwards too. And the second thing was they were squeezed at both ends. They were too quick, but then they were far too close to high TC, which was discovered in the year that they published this result. So this paper or this result probably only got, 6 months in the sunshine. And if it had been done different by 10 years either way, it would have probably been a lot better known. So, good. This makes it look, and it is true, that the Haas-Van Alphen effect is this wonder technique that can help us understand every metal in existence. Unfortunately, there's a catch. And this was worked out, this is the St Andrews contribution to the Haas-Van Alphen, because Bob Dingell was the professor of theoretical physics at St Andrews. And he realized that disorder gave us this gift of what I call the evil exponential. It's the bane of the life of everybody who works on DHVA. And what it says is that disorder broadens the density of state spectrum itself. So it's not like thermal broadening, which is broadening the Fermi function. The disorder is broadening the Landau levels intrinsically, and that comes in this exponential form, where the argument of the exponential is the ratio of the cyclotron radius times pi to the mean free path. And let's see, now Steve Julian, who taught me a lot about DHVA as we worked together in the 90s, he said the one thing that you really get if you work on DHVA is an appreciation for the meaning of a nonlinear function. And let's put in some numbers and look. So a typical metal would have that kind of KF. Nowadays, a big superconducting magnet can give you 20 Tesla. So let's imagine that you have a really fantastic material guy working with you, or in Gil's group, we were the materials guys, we had to do it ourselves. And you'd produced a material with a mean free path of 1,000 angstroms. Certainly in uranium platinum 3, that's enough to make you pretty damn proud of yourself. That exponential there means that you have experimental access to about 6 parts in 1,000 of the thermodynamically available signal. Okay, but then imagine that you're working on some new complex material and you or your colleagues make a single crystal with a mean free path of 100 angstroms. As a materials person, you're not totally dissatisfied to have done that. As we all know, there are materials with far shorter mean free paths than that. Unfortunately, for DHVA, it matters, right? And so in order to take DHVA to the regime of studying complex, interesting materials of the late 20th century, we were going to need huge magnetic fields, excellent signal to noise, or fantastic materials, or both. And as Louis Taillefer said at Gil's 60th, the most important thing is that one. You have to persuade people And Gil was very adept at that, persuading people to take on challenges that if they'd known just a little more, they wouldn't have gone anywhere near. So the analogy I like is it's like you give you a metal detector and they say, go and look for a needle in the haystack. So you're applying your metal detector to the haystack. But a priori, you don't know whether you're looking for a needle or a piece of metal of about a nuclear dimension, right? And so, it's a yes-no experiment. And the answer is no much more often than it's yes. And this is part that takes me back to what I said in the introduction. The drive to be able to do these experiments really drove huge improvements in high field technology, huge improvements in materials technology, as well as the theoretical developments I told you about before.
And huge developments in the gullibility of graduate students?
As we're going to see, this graduate student had done some work outside condensed matter physics before starting, so he quit his PhD project after a year. But I'll tell you why. But before that, I want to take our theorists and make them appreciate experimental physics. Because the rig that Gil and Steve Julian and colleagues set up, which is still 25 years later the benchmark, now it's been repeated various places in the world, it's still the benchmark. You want a base temperature of 10 millikelvin or so, sometimes even lower. Sometimes some of these rigs are now going down to 1 millikelvin, although that's challenging. You want a noise floor of the level of picovolts per root hertz while you're at your base temperature and while you're at a field of 20 Tesla. And doing these things individually isn't particularly hard, but doing them all together really isn't easy. And the advantage is once you've set, and this is not Gil's system, this is a baby system that we built in St Andrews that gives some illustration of what it looks like, but the Cambridge one is more impressive than that photo, I can assure you. So, my PhD project, as Mr. Gullible coming in, was to find quantum oscillations in the high TC superconductors, to find them in the cuprates. So after a year or so of that, I had enough experience to realize that this certainly wasn't going to happen during the lifetime of my PhD, if during my lifetime at all. And so I moved and did some other things, but we always had our eye open for materials which were at least similar to the cuprates, which seemed to be pure enough where you could really do an experiment. So this material, strontium ruthenate, came along, and we were able to do that experiment. Here's working with Steve Julian. This is work from my postdoc, where this is our particle physics. So here's our quasi-particle resonances. And we were doing this experiment, and of course, in the end, it comes down to 6 months' work to set the fridge up and the electronics and everything. And you come down to basically you're plotting a transduced voltage on a screen, and you're sitting there one day, and all of a sudden that signal starts to oscillate in a way that after a few oscillations you can convince yourself it's not noise. And the exponential can work with you, because if it's on the right side of you, the signal that you end up getting can be a lot bigger than you feared it might be. And in this case it was. We could really see it. So you're seeing quantum mechanics happen on the screen. We were already very excited. Then the excitement increased because the great man appeared in the lab the next day because he'd heard what was going on. And he said, oh, wow, oxide, this is amazing. And David, throughout his life, kept extremely careful notes in a series of lab notebooks. This one from 1937 is where he was working out how to do the best torque magnetometry. They have lots of history of this. By 1995, his handwriting wasn't as neat as that. He was about 80 years old. But he was very enthusiastic. And so after saying, oh, this is interesting, the next day he came into the lab and he put 4 A4 pages of tightly spaced instructions down about here's all the interesting things you guys should do. And we were thinking, oh, this is fantastic. I can't believe David Shoenberg's actually interested to this level. So we read it and we thought, well, if we work for a month, we can probably start to deliver on some of these demands. So that's okay. So the next day he came back and there were 6 more pages of tightly written script plunked on the table. And we let this go for about a week. And then we had to decide that there were 2 choices. Either we did an experiment or we listened to what David was asking us to do. And I'm deeply ashamed to say that we locked the lab door from the inside to pretend that it was running on automatic while we carried on with the experiment, because it was the only way we could possibly finish it. Finish it we did, and so we kind of managed to establish the Fermi surface of strontium ruthenate, and that was all very rewarding and very nice. But it was kind of just bringing back into focus our persistent failure to find oscillations in the cuprates. And when you're kind of hearing about all the experiments that work, between us, Steve and I, working together, we'd probably put 9 months of dilution fridge time into very, very high signal to noise and completely unsuccessful searches for those oscillations. So we thought, okay, we can do it in strontium ruthenate. Let's go back and think even harder about how to do it in the cuprates. So in the cuprates, here's the phase diagram. Please don't fight with me about the diagram. It's just an illustration. What we can say uncontroversially for this talk is that if you're near the maximum in TC, your critical fields are so high that you can't possibly try the Haas van Alphen. Or at least you certainly couldn't in those days. So you were going to have to either work when TC was low on what's called the underdoped side, or high or low on what's called the overdoped side. So Ruixing Yang and Walter Hardy and Doug Bond were doing fantastic work at UBC on working out how to make pretty high purity underdoped crystals. And we were doing clumsy but well-meaning attempts to grow thallium, barium, copper oxide crystals, where there's inevitable disorder, just the thermodynamic state is not stoichiometric. But it's a kind of heterodoping. The crap is happening not in the copper oxide layer, but somewhere else. So you were able to get, we knew, reasonable mean free pass, several hundred angstroms. And the question was whether experiments were possible or not. So off we went to the lab at Bell Labs of Greg Bollinger, who many of you now know is the head of the high field lab in the States, and who was 60, or whose 60th Festschrift was last week. But this was before he was Mr. Big. He just had a small lab in Bell Labs, but he was he was leading the world in fields achieved at that point. And the idea is rather simple. You take a capacitor, you charge it up, you hit a switch, you discharge the capacitor through your coil, and as you discharge, the current passing through the coil to ground gives you a high rise time to some maximum field, followed by a slower but still pretty quick fall time, and you take data during that fall time. And the picture I'm showing you there doesn't reach 60 Tesla, but actually Greg was able in those days to reach 72 as his peak field. This was 25 years ago, and 60 Tesla in a way that we got a few shots out before the magnet exploded. And the magnet exploding in these things is an ever-present danger and quite a spectacular event. So we went and we studied the resistance of thallium, barium, copper oxide. And Greg had built this rig to do fractional quantum Hall effect work. So he'd optimized everything to measuring very high kilo-ohm resistances. We're all of a sudden bringing a sample to him which was presenting him with milliohm resistances. And we made the unpleasant discovery that while we could produce oscillations, they certainly weren't quantum oscillations. So the noise levels in those days were far too big for us to be able to get to a reproducible signal. So we published something on it, but the experiment essentially failed. But it didn't fail in the long run because it really motivated Greg to declare war on noise. And he put in a lot of work to improve the high field facilities of the US in their noise performance, periodically, all the way to where we now have, they're absolutely fantastic, probably 10,000 times better signal to noise now than they were in these experiments from the 90s. So I was, not too disappointed with this. Strontium ruthenate had calmed me down a lot. We'd at least done one experiment in my whole life. But others, and I wasn't even pushing it that hard, but others were pushing it hard. And although Greg was trying to take the whole American effort and turn it into the signals and noises that we really needed, it's a little bit like these entrepreneurial things where a small company comes in with a bit more flexibility to get things done quickly, and a couple of inspirational people manage something. And in particular, this guy Cyril Proust was working in Toulouse at really, compared to the high field labs in other parts of the world, a very small facility. But he was working, and he got up to 60 Tesla as well, but he was working really hard on the noise level. And there's a picture from his lab, which I think you might enjoy. So here's the principle. shut switch, discharge capacitor through coil. So the coil's sitting somewhere here below the surface of the room. But that's what's below. That's the capacitor. Right? And so these pulse field experiments are not entirely trivial. And Cyril worked away, and he was getting to the stage where he believed he had a very good signal to noise in the pulse fields, at least 1,000 times better than the one I just showed you. And he'd done a postdoc with Louis Taillefer. Louis is a visionary. Louis is the kind of guy who will not give up when there's a potential experiment. Well, he's not a coward like me. So he insisted that they go back and look again at the cuprates. And in these underdosed cuprates from Doug Bon and Ruixin Liang, they saw the first cuprate quantum oscillations in 2007. Exactly 20 years after I began the PhD as a gullible student who was told to do this. So I could have had extremely grey hair by the time I graduated if I'd listened and not been a bit tough. This was a wonderful experiment. And it, in turn, re-energized my friends from Cambridge postdoc and grad student days, Nigel Hussey and Tony Carrington, who got in touch with me and said, look, dust those crystals of yours. I'd made the crystals. Dust the crystals off. But we're going to go back with Cyril. We're going to try and find the damn oscillations in thallium-2201. So I said, fine. If you want to go and work hard for weeks in working shifts at a pulse field lab for no gain, that's up to you. I'll certainly give you the crystals. So they went away and they measured the resistivity, which is showing here. There's the superconducting transition of these materials, or the resistive transition. And in the simultaneous measurements, more or less, they measured the magnetic torque as well. So this irreversibility of torque is all to do with superconductivity. And if you look at these data, you don't see that nirvana has been reached. But if you blow up the data from about 55 Tesla onwards, that's what you find. You find these beautiful and entirely reproducible oscillations. And the jammy buggers got this all in one weekend of work. So they took the crystals and then they phoned me and I was at home and Nigel went, we're going to send you something. You're going to be surprised. And I was, and it's a beautiful experiment. So this again tells you just what quantum oscillations really look like. You're always looking for that needle in the haystack. You're looking for the signal right down towards your noise level. Okay, so this was again, for the three of them, I think this was a fantastic achievement. So I always like to, as you get older, it's nice to know that experimental science progresses. So let's examine that progression, thinking about this experiment on the thallium-barium cuprate. Those are the relevant parameters. And so Cyril and Tony and Nigel, they had 60 Tesla. They had a fractional noise of about 2 parts in 10,000, which is incredible at 60 Tesla. That's what Proust's achievement was. They had, at that mean free path at that field, they had about 1 part per 1,000 of available signal relative to the thermodynamic limit. And so they had a signal-to-noise level of about 6, and that's what we saw in those oscillations just now. So now this is a bit of self-justification. In the failed experiment that we did 10 years before, we had the same field, so we had the same observable oscillations, but we had about 1,000 times poorer signal-to-noise, so we had no chance of seeing them. In the work we did in the early 90s that never got anywhere near publication because we found nothing, Steve and I had 18 Tesla. We had, thanks mainly to his work, a fantastic resolving power of 1 part per million, but we didn't have the field. We had 10 to the minus 10 of the possible observable intensity, so we had even less chance than we'd had in the Bollinger experiments later that decade. So now it's entertaining. Start thinking about this. What chance did the Haas and Van Alphen in 1930 have of making this experiment work? I'm not going to say yell out and guess, but there's the answer. They really were struggling a little bit for their signal-to-noise, right? And so experimental physics does progress. And that then, of course, I think it should beg the question in some of your minds, well, how on earth did they discover the Haas-Van Alphen effect in 1930 in the first place if they had so little chance of doing this experiment? And that's something of modern relevance. The answer is that they worked on bismuth, which is a semi-metal or a very low-density metal. Kf is tiny, And it's quite pure, they probably had 1,000 angstrom mean free path. So for those parameters in bismuth, they had about 60% of the thermodynamic signal available to them, when they had 1 part in 10 or 3 parts in 10 to the 90 of it available to them in thallium-2201. Again, the meaning of a nonlinear function, right? And that's of relevance today because semi-metals are back in vogue. And it's kind of galling for me because every man and his dog and woman and her dog is able to do the Haas van Alphen or Shubikov-Haas experiments. But none of these facts have changed. They're only doing it as a routine character tool because they have an exponentially larger signal to be looking at than the people who are trying to do large density metals or heavy fermion metals. And so, don't be fooled. And in many materials, you have some very small orbits and some large ones. The large ones determine the thermodynamic response. And people don't really understand that in the same material, if bismuth had both the large orbit and the small orbit, you could be seeing something and feeling very good about yourself, and you could be a factor of 10 to the 80 away from being able to see the thermodynamically relevant information. So this is still a pretty remarkable technique. Okay, I've kind of gone on with time, so I'll say this and I'll skip over the very last bit. So now we're on to what the future might hold. And one of the things that we're now able to do is to use microstructuring techniques to take very pure single crystals and cut them into any experimental form that we want. And this was an experiment with a very accidental result that Philip Mahl and Karsten Putzke and my ex-student Maya Bachmann, who's now working in this department, they were trying to measure the C-axis resistivity of a very pure layered compound. Right? And so they were passing current this way, and because they could, they applied a perpendicular magnetic field. And what they discovered was that superimposed on the normal magnetoresistance, they saw very well-resolved oscillatory behavior, but that oscillatory behavior was periodic in field, not in reciprocal field. And they also realized that they saw a different frequency when they made the same kind of device with different channel width. So Philip, within about 2 days, made and verified a really adventurous hypothesis. He said, what if these are Aronoff-Bohm-like oscillations? But what if the loop we should be thinking of is a real space loop comprising the entire width of the sample, which is several microns, so it's quasi-macroscopic, and one interplane separation, which is just a few angstroms. So what if you had some very anisotropic loop in your mind like that, and that this period was being controlled by the Aronoff-Bohm flux going through that real space loop? And because we've got very good control of the materials and very good control of the devices, we were able to check that to high precision, and that's exactly phenomenologically what is going on. There's the dotted line corresponding to the hypothesis. The points are data from different devices. So there seems to be no doubt that phenomenologically what he was thinking is correct. Thing to say is that that biggest device there is 12 microns wide. In this material, that's about 50,000 lattice spacings. So you seem to have, in a metal, really coherent, real space, not field controlled, but dimension, a device dimension controlled, coherent interference going on over 50,000 lattice spacings. And I think, we'd already been amazed at the purity of these particular layered metals. This is a very good manifestation of it. It's a very surprising fact. So, to the best of our knowledge, nothing like this has been seen in any layered metal. So we got excited and we sent it to be published. And it got sent back to us because it was rejected because there was no theory. You can't publish anything like this without a theory. So we worked with Roderick Mersner and Takashi Oka at the institute next door. And they came up with, it's a half theory, it's a beginning theory, but it's a categorization that makes people feel more comfortable. And it has it's something to do with the anisotropic Hofstadter model, and it has a beautiful analogy with quantum optics. So we wrote this, we were very happy, and we got a great referee, a kind referee. He said, oh, well, in that case, that's just like a Josephson junction would behave, how a Josephson junction would behave, so there's nothing new here. So Roderick Mersner, I guess he spent some time in the department. He's a great character. So he responds to this saying that nothing at all, except that we don't have a superconductor, a junction, or a Josephson effect. Now, writing that back to a critical referee may be good for short-term satisfaction. It may not lead to long-term fulfillment. But anyway, that's our response to that comment. But you've got to love the refereeing process. But this referee then also said something which I think is a very beautiful thing and a nice way to end the talk. What the referee said is, I don't understand, I want to see, this is your orientation, and you've got this Aronoff-Bohm type oscillation. What if you change the orientation to having the field along the current, and therefore you had a field which was giving you ordinary cyclotron motion in the planes? How do these oscillations relate to what would happen there? So, in other words, in your dreams you would say, I've showed you that this is a quantum oscillation periodic in field because it's controlled by a real space dimension. But this is a traditional quantum oscillation. So if you've got that, we go back to this original real space thing I was telling you about, and that if the field is big enough that the cyclotron motion is confined within that small device, then you should be back to periodic oscillations, periodic in 1 over b, because it's the magnetic length which is setting the length scale instead of the device size. So we did that experiment, or they did that experiment, and the result is just, I don't know, so didactic. So this is the angle gamma. So when gamma is low in this definition, we're in the Aronoff-Bohm regime, if you like, the mesoscopic regime, and we always see the field periodic oscillations. Then we change gamma to get to be bigger, and so we're rotating the field this way. And at sufficiently high field, we see these oscillations, which are actually periodic in reciprocal field as expected. So this is the bulk physics limit in this device. This is the mesoscopic quantum oscillation limit in the same device. And amazingly, that dotted line is not a purely fictional choice. That dotted line is them plotting out the criterion for when the first cyclotron orbit at that field gets to be within the sample. And you actually see a kink in the resistivity where that happens. So there's a physically measurable thing saying that you're confining the cyclotron orbit into the plane of the device. And you see a kink in the data. And you can even find an intermediate angle where you go from the mesoscopic region through the kink to the bulk region, all by sweeping the field in the single device at a single angle. So I think that to me that's very didactic. That really helped me give this talk because it helped me to understand the meaning of the reciprocal field oscillations and the magnetic length scale as opposed to an externally controlled length scale. So I think that's part of the future. The other part of the future, which I'm just going to go over very briefly, not at all in fact, is that incredibly there are some insulators brought to us, Ted was 50 when he published this paper, or so, brought to us by Ted. There are some insulators in which it's now been proven that you can see the de Haas-Van-Alphen effect even when you're in a non-metallic state. And there's a lot of, euphemistically put it, debate still going on about that observation. I personally think the observation is true. And it stimulated some very innovative theory showing that the metallic interpretation of quantum oscillations in DHVA, while true, isn't the end of the story. There are other ways and other circumstances in which you can see the de Haas-Van-Alphen effect. You don't actually always need a metal. So that's going to be another part of the future. And if you notice, the temperature dependence of the oscillations has this massive deviation from the Lifshitz-Kossovich prediction. So there you're seeing this idea that the Fermi liquid existence proof is failed, but you bloody well hope it's failed because this is an insulator, it's not a metal. So I've talked on longer, I hope I haven't bored you too much. There are my conclusions, I'll leave you to read them. I'll stop talking and thanks very much for your attention.
So questions?
So to what extent
extent has the Haas and Alphen been used in cases where Schoenberg of the Haas shows fractional field?
Okay, so the whole way that I gave this talk was hidden behind a sentence that I put in carefully saying that all the interpretation is correspondence principle interpretation. It's valid at high quantum numbers, right? And so everything I was saying today was to do with high quantum numbers where that kind of fractional effect doesn't happen. There's, of course, tremendously interesting things go on at low Landau level, low quantum numbers. Usually that's seen in just two-dimensional electron gases. There are very few electrons in there, so making a magnetization measurement is extremely difficult. Not impossible, but in general, the transport way of probing those effects so far has proved to be more fruitful than magnetization, just because of lack of electrons.
So when you showed the Erno bomb effect,
Yeah. Yeah, we only see, we of course have looked very carefully for higher harmonics for skipping over two layers, but we don't see it. We only ever see fundamental. And I should really say that while we have, you know, enough of a model to apparently stop referees complaining, we don't regard that as a theory. There's plenty of things which are extremely strange here. Among them, the fact that what we see here persists to 50 Kelvin, and it's very easily visible in 60 Tesla as well. So, the persistence to 50 Kelvin knocks many of your preconceived notions of how you're going to explain it actually out the window. I think it's an interesting theoretical problem.
So I'm inspired to tell a story from the conference that we were both at with Greg Bollinger concerning his 60 Tesla magnet. So as Andy said, his 60 Tesla magnet was designed to be able to probe the fractional quantum Hall effect. The idea was that you could access lower fractional fillings by going to higher fields. It was a good idea, except he had the disadvantage that he was fighting against people making better materials, who made lower electron density materials. They reduced KF. And so it became much better to do the experiments at lower fields with lower electron density. So
yeah, so he was rendered obsolete instantly
forced
to work with characters like me. Yeah.
Exactly. Are there any other questions? All right, let's thank
I thought there was one there, yeah.
Are there other experimental examples where the Fermi liquid temperature scaling fails, but you know it's also metallic?
Yes. As a couple, there's an experiment on cerium, cobalt, indium 5, heavy fermion layered superconductor. There are subtle issues.
So where it doesn't fit Lifshitz.
Where it doesn't fit Lifshitz-Kosovic. So this is work from Steve Julian and Alex McCollum. You have to be very careful because I've hidden under the rug things like interference between different spin species in these experiments. And they put a very conservative interpretation on what they're seeing. But it's a kind of contrived model, in my opinion. I think there's a decent chance that that actually is a breakdown of Fermi liquid theory, and it's one of the places where you might expect it. But I mean, it's one of the holy grails of anybody working in this area. Actually, I took a slide out for reasons of time. There are quantum critical phase diagrams where you can go as a function of tuning parameter from Fermi liquid at low fields to a different Fermi liquid at high fields. And then as you come down, there's a quantum phase transition or a continuous quantum phase transition in between, right? So there, at finite temperature, there's some width of parameter space where you believe you don't have a Fermi liquid metal. But there, in a sense, that's another disadvantage of DHVA, because DHVA has very low energy scales, which is fantastic for some things. But if it's a heavy system, you can only work at extremely low temperatures. And if you're working at extremely low temperatures, the range of tuning parameter where you think you have an unusual metal is extremely narrow. So finding that optimum window of a temperature and tuning parameter, area of phase space or region of phase space where you can work is one of the challenges there. But you know, all the groups who are doing DHVA seriously are thinking about exactly that problem. And in cerium, cobalt, indium-5, my own prejudice is that maybe that window just existed there for fortunate reasons. But you know, I have huge respect for Steve, and he would probably, if he ever sees the video of me saying this, he wouldn't be happy. But that's, I'll stress, that's my own opinion.
All right, let's thank Andy for a really beautiful.
You probably want to take off the microphone before you